Hi there, welcome back. In this video lesson, we will deal with copulas. Copulas are a very important tool, a statistical or probabilistic tool that we can use to approach multivariate distributions. Now, I cannot assume that everyone in this course is aware of what a copula is. So in this video lesson, I want to share with you the basic knowledge that we need in order to move on together to the multivariate framework, to the portfolio framework. So, a copula is a function used to describe the dependence between two or more random variables. With copulas, we aim to represent the joint distribution of a random vector. In the copula approach, the copula describes the dependent structure among the components of the random vector, while their marginal behavior is contained in their marginal distributions. Models like JP Morgan's credit matrix rely extensively on copulas when we consider their portfolio extension. That is to say, when we have a portfolio of exposures that may default. Survival models like the Lee's model, a model we will consider together next week, again, rely on specific copula assumptions. And many of the formulas you know under the Basel framework, for example, in the internal rating-based approach, actually derive from the assumption that we are using copulas to model the joint distribution of defaults. But in order to efficiently introduce copulas and their properties and their basic theorems, we need first to introduce the concept of generalized inverse. The generalized inverse is a special function that you probably already know in its basic definition, and we need two important quantities of this function in order to proceed. The generalized inverse is an extension of the concept of inverse. It is a generalized quantile function. If a distribution function is strictly increasing and continuous, the generalized inverse coincides with the standard quantile function you are probably used to. For us, the most important properties of the generalized inverse are the quantile transformation and the probability transformation. The quantile transformation tells us that the quantiles of a uniform random variable with support on the interval 0, 1 can be linked to a distribution function g. In fact, the probability that the generalized inverse of u is smaller than or equal to a value y corresponds to g of y, where g is the distribution function on which we have defined the generalized inverse. The probability transform tells us that whatever continuous distribution function g is distributed according to a uniform distribution if we treat it as a new random variable z equal to g of y. We know that the distribution function takes values in the interval 0, 1. To prove it is uniformly distributed, we can play with the generalized inverse, as you can see on the screen. I do not want you to learn the proof by heart. Just remember the possibility of moving from a given distribution function to the uniform one. Consider a random vector x1, xd with continuous marginals f1, fd. If we apply the probability transformation to each component, we obtain a new vector with uniform marginals. A copula for x1, xd is defined as the joint distribution of the new uniform vector u1, ud. The most interesting aspect of copulas is that we can show that the function c contains all the information on the dependent structure among the components of the random vector, while the fi's necessarily contain all the information on the marginal distributions. SKLAR'S theorem is the most important theorem for copulas because it's the theorem that tells us that we can always give a copular representation of wherever joint distribution. So it's a very important result. and always SKLAR'S theorem tells us what are the conditions we need to fulfill in order to have a unique representation of our joint distribution. On your screen, you can read the text of SKLAR'S theorem. We do not prove it. The summary of the theorem is: every joint distribution has a copula representation. If the marginal distributions are continuous, then this representation is unique. In other words, there exists only one copula function that can represent the dependent structure. If margins are not continuous, then we can still find copulas, but they are not uniquely defined. For those of you that like to play a little bit with mathematics, here an exercise. It is a simple way of proving that with discrete marginals we cannot have a unique copula. An interesting property of copulas is the existence of bounds. These are called FRÉCHET'S bounds. Every copula C is contained between W and M. The upper bound M is known as the comonotonicity copula. It represents the case of perfect multivariate positive dependence, when all the random variables can be expressed as linear combinations of one of them. Remember that under comonotonicity, the value at risk is coherent. It is one of the few cases. The lower bound W is not a copula, not in general. It is a copula only in the bivariate case, and in that case it is called counter-comonotonicity copula. It represents the case of perfect negative linear dependence. There are different examples of copulas we can take into consideration. For instance, the independence copula, that is the copula characterizing the joint distribution of independent random variables. As expected, it is the product of the probability transforms. We then have the Gaussian copula. This is the most important copula for us. It is the basis of some IRB formulas and important models like the LEAS one. We will discuss pros and cons of this copula. For the moment, just remember that under the Gaussian copula, all the information we need about the dependence is in the correlation matrix. We do not need anything else, and dependence is only of the linear type. Please notice that a multivariate Gaussian or multivariate normal and a Gaussian copula are not the same thing in general. In a Gaussian copula, the marginals we take into consideration can be of whatever type. There is no limitation in practice. For what concerns the multivariate normal, on the contrary, the marginals are necessarily normally distributed. Okay, so this is a quite important difference. Necessarily, if we start from normal marginals and we apply a Gaussian copula, what we obtain is a multivariate normal, but this is a special case. As you can imagine, we can define a plethora of possible copulas. This is very nice in terms of flexibility when fitting data, but it also opens the non-trivial problem of model selection. Okay, I think it's enough for the moment. We will introduce extra material about copulas when we need it. My suggestion is to try to solve this exercise. The solution will appear in a couple of weeks on the course platform. Obviously, this is just an optional thing for you in order to make you a little bit think about copulas. So that's it. Goodbye. See you next time.